All right, welcome. All right, so we are looking at different approaches to build concurrent servers and write concurrent applications. And there are trade-offs. And we're trying to understand these trade-offs. So in the process-based, we have a process, we fork a process for each client, and each client process has the entire virtual address space. There is no sharing. The scheduling is done by the kernel, which is a good thing. So as a programmer, if you look at the process-based server, the code, it's really simple. You just fork a process each time you get a client request. But there is no data sharing. What if we have a scenario where clients want to share data? So we tackled that problem with the event-based server, where we have only one process, and the programmer manually interleaves the execution of different clients by using I/O multiplexing. Using the select system call, we monitor which clients have some activity on their descriptors, and then we take an action corresponding to that specific descriptor. The programmer has to do a lot more work. You might have noticed that echo server s.c is quite complicated in this week's lab. There is only one. The other drawback is that I cannot exploit multi-core processes with the event-based server because there is only one process, and the programmer is doing the scheduling. The good thing is there is sharing. There is a possibility of sharing of data if multiple clients want to share data with each other. Now, in our Echo server, there is no such thing going on because it's a really simple application, but there are real-world applications where we want sharing among the different logical flows. Each client is a logical flow with its own sequence of instructions that the programmer here is trying to interleave. Now, today we are going to look at what is predominantly used today to build concurrent applications, thread-based servers. So concurrency and parallelism using threads will be probably the last thing we do in this course, this week and next week. The good thing is the abstraction of threads is provided by the kernel. Just like processes, the kernel is responsible for scheduling or interleaving the threads of execution onto the processor or processors or cores if there's a multi-core processor. So the programmer's job, once again, on the scheduling side, on the interleaving side, is pretty straightforward. We will just create a thread for each client, and we're done. We leave the kernel to do the scheduling. The question arrives, so why do we need threads? Well, the good thing is that all threads run in the context of a single process. So threads can share data. It's a hybrid of the above two approaches. The other good thing is that threads can be scheduled by the kernel on multiple cores of a multi-core processor. So there is parallelism here. And as we will see today, threads are lightweight. What do I mean by lightweight? It will become clear in a little bit. Processes are really very heavy in terms of when you want to do a context switch, you have to do too many things. A process has an entire virtual address space, file tables, VM structs, IO tables, IO structures. There's too much fat associated with the process. And there is too much to save when a process has to be context switched in place of another process if we have a single CPU. So we are going to use threads instead of processes. In this week's lab, you are doing some practical exercises with the first two approaches. And next lab, the last lab, will be threads. So here's what a process carries with itself. It has a context, the register file, the registers, condition codes, stack pointer, program counter, or instruction pointer. The structures that are used by the kernel to provide the virtual memory abstraction, a table of descriptors, the break pointer associated with the heap, and then on the right, we see that there is how the virtual address space looks like. There's a heap, there's code, data, global variables, shared libraries, this and that, and whatnot. All these things we have touched upon in the previous lectures. They form the context of a process. Together, they distinguish one process from another. This is a process context on the left and code data stack stored in memory on the right. This context, the red part, is something that is very closely associated with the CPU. The program counter, there's a register that stores the program counter, the stack pointer, condition codes, register file. And then there's the green part, which is the data structures stored, managed by the kernel. So this is the process context. And if we want to schedule another process, we have to save the green part, the red part, ensure that we don't mess up with these structures. What we can do, and what we do with threads, we take some portion of the context and we have what we call a thread. So here's a main thread which has a stack pointer, and the context of the thread is just the red part. The register file, condition code, stack pointer, program counter, that's it. So each thread will have its own stack, its own stack pointer, a program counter, condition codes, register file, that's it. All the kernel data structures, all the kernel context is shared by all the threads. So we have created a new abstraction. With multiple processes, each process has the red part and the green part. The kernel context, the program context, everything. Every time we create a child, remember, we copy all the VM structs, all the tables, and the child inherits the data structures of the parent, and initially they are all the same as the parent, and then when the child updates, blah, blah, blah. All of that is now gone. It turns out that we can have a lightweight version of a process, lightweight version, this new abstraction called thread, where each thread will have a stack that is local to the thread. We want, no other thread can touch it. Well, actually, you can touch it, but at least the conceptually, you should not. So each thread has a stack pointer, its own stack, its own version of the register file, condition codes, stack pointer, program counter, and then all threads share the shared libraries, the runtime heap that you built in assignment 1, and the kernel context. All threads will share a large portion of the data structures that are used to create a process. And only a fraction of the things on the left are local to each thread. Now things are a lot more easier when, in terms of managing threads, it's much more easier than managing processes. Processes carry a lot of other stuff with them. Okay, so now we have threads that share the heap, the code, the data, the kernel context, but they have their own stack and registers. So multiple threads can be associated with a single process, and they can share the kernel data structures and shared libraries, like I was saying. So each thread has its own logical control flow. Each thread has a thread ID that is used by the kernel to distinguish a specific thread, to distinguish different threads from each other. And very importantly, each thread has its own stack, but basically it's just one stack. We just have multiple stack pointers to ensure that we know where each stack is, what portion of it. It's one region in the virtual address space, and we use pointers, stack pointers, to give each thread a portion of the stack. Okay. And now I can schedule these threads on a per client basis. I'll soon show you an API to do that. I don't have to fork anymore. And this will give me the sharing that I need and the parallelism that I need. And on top of everything, they're lightweight to carry around. If I want to save the context of one thread and schedule another thread, all I have to save is a register file, condition codes, really small things, one program counter, one stack pointer, and hopefully the stack itself is preserved in memory as long as we remember where the stack pointer is. So the takeaway is threads are a lightweight abstraction given by the kernel. So multiple threads, multiple logical control flows can share data on the heap in the kernel. And so this is the third approach to write concurrent servers. So unlike processes, which have a strict parent-child hierarchy on the right, we looked at that. Threads are all peers. They're all peers of each other. There is no, so these two threads are peers. These two threads, they can cancel each other, wait for each other, reap each other, unlike processes where there's a strict hierarchy. You parent can reap this child, that thing, that. And they all share, all threads share code, data, and kernel context. Now we have to be careful when we write threaded programs. As you know, in C, at least, you have ways to get around. You can mess with someone's stack, and we will see how we can do that. So there are problems with sharing when you share things, and we will see how you have to be careful with sharing variables and all that. If multiple threads want to access a single variable, account variable, to do some kind of accounting, so each thread is doing some counting and wants to update a counter, we have to now ensure that the two threads are not doing it at the same time. And this will lead to a lot of synchronization problems, where we will spend most of our time in the next 2 weeks. So like processes, two threads are concurrent if their flows overlap in time. Otherwise, they are sequential. Now, I want to spend some time here. Concurrency versus parallelism, and concurrency is still a little bit confusing. I see that. So thread A begins execution at this point. Let's call this point X. And at point Y, it stopped for a while for whatever reason. Maybe it executed, performed a system call that required reading something from an I/O device. So the kernel decided, hey, I'm going to context switch it out, and I'm going to do something else while the disk read is going on, which is really slow and all that. So the execution, so let's call it X1 and Y1. And let's call the execution, when the execution of thread B starts, let's call it X2. And when it ends, call it Y2. Now we can clearly see that the execution of A and B overlap in time. The duration of time from X2, between X2 and Y2, overlaps with X1 and Y1. And that's why A and B are concurrent. They may not be running at the same time because, for instance, if we only have one processor, they may not be running at the same time. A runs, then B runs, then A runs, but this is concurrency. Two control flows of execution are active, alive, and their execution overlaps in time. Similarly, A and C are concurrent because their execution overlaps in time. But B and C are not concurrent. B ends here. This is where B ends, and this is where C begins. So there is no time when B and C overlap. Now, if we are on top of, so A and B are concurrent, that's for sure. If we have two processes and we are able to execute A and B at the same time, on top of concurrency, we also have parallelism. And that's a distinction between, that's a difference between concurrency and parallelism. If you also have two CPUs to execute both A and B at the same time, we also have concurrency. Oh, sorry, parallelism. So here we have A and B are executing on two different processors or two different cores of a processor at the same time. Not only are they concurrent, they're also parallel. They're running in parallel. And here we are just interleaving A, B, A on a single processor. So threads and processes are similar because each has its own logical control flow. Each can run concurrently with others. And we can do the context switch of a process, and we can do context switch of a thread. But they're different because threads share all code and data, except the local stacks, except the program counter, except the condition codes. Those things are preserved on a per thread basis. And threads are less expensive than processes. So process control, creating, reaping is twice as expensive on Linux as threads. Anything to do with threads is much cheaper because there is less information that is associated with a thread. So we will study p-threads or POSIX threads, which are widely used, popular. This is one library or one API that gives us the ability to create and use threads to write concurrent programs. So we have a number of functions: pthread create, pthread join, pthread self. You create a thread using pthread create. You reap a thread using pthread join. And just like get PID, here we have pthread self. So a thread can get its own ID. threads can cancel themselves or other threads. And then to synchronize access to shared variables, we will use what are called mutexes or semaphores later on. So we can log certain variables, so only one thread can update the variable at any given time. Otherwise, things can mess up if two threads try to do the same thing to the same variable at the same time. There are no guarantees what will happen. So let's write a hello world program using pthreads. So threads are the most relevant to your assignment too. You won't be writing process-based or I should not say that. You're not going to do this week's lab. No, forget what I said. Don't worry. Everything is relevant to your assignment. So I want to create a new thread. So the type pthread t under the hood is just an integer. So thread ID is a variable that is used to identify a thread. So what I'm going to do is I'm going to use pthread create to create a thread. I'm going to pass the address of the variable pthread t that I created. And when pthread create returns, it will use dereferencing to fill TID with the integer of that the kernel assigns to this thread. You can change certain behavior of a thread by changing something called attribute variable. We're going to use null here in this course. So then we're going to pass a pointer to a function. So function pointers will now become relevant. And this is a function pointer. This is a pointer to a function that takes a generic pointer as input and returns a generic pointer. All right. So you can pass arguments to tell the thread what to do using the generic input pointer. Okay. And when the thread is created, it will run this function. And it will use the arguments that are passed to it when the thread is created. And this function, thread, just like any function, has its own local stack. Okay? So this is how threads work. When we create a thread, at the same time, we have a function. In this case, it's just a printf hello world. And I want this thread to printf hello world. The way I'm going to make it do it is I'm going to pass this pointer to this function to the call to pthread. And when pthread create returns, the function thread will start running.
Where does the return value of the function go?
So let's see in a little bit. There's code to show that. So we have a thread ID that we pass a pointer to the type thread ID, which will be filled by the kernel to tell us what's the ID of this thread the kernel assigns. Okay, we're going to use null. We don't use any special attributes. We want our threads to just do the default things. We're going to pass an argument to the thread routine. And the last variable, the last argument is how we pass the thread arguments. And so when we reap a thread, we use pthread join. When the thread exits, so the main thread here, or the main process, Actually, once you create a thread, everything is a thread. So we say that we have a main thread and a peer thread that we just call thread. So the main thread here is going to wait for this function or this thread to exit, and we get the return value, whatever is returned by the thread, as a second argument of pthread join. Okay, here we are just ignoring it. If we pass a data structure or a pointer to a structure, we can then fill up that structure in the thread routine. Okay, let's see an example of that in a little bit. So we have the main thread. At some point, we create a peer thread. When pthread create returns, the main thread calls pthread join. This is equivalent to reaping a thread. When the peer thread does a printf and returns, terminates, pthread join returns. So pthread join is like a barrier. It's waiting for the peer thread to terminate. All right, and then the main thread terminates as well. So pthread join is a little bit different from the wait page and other system calls that we use to reap a process, because you need to explicitly tell pthread join which thread exactly do you want to reap. So with processes, we had a bit more flexibility. We can just call wait page, and whenever a child terminates, we'll wake up. So here we have to be explicit about which thread exactly we want to reap. All right, so we're going to look at the concurrent echo server. So like before, so once again, we have the listening file descriptor and the connected file descriptor. And anyone notices a difference compared to process-based server and event-based server? What type are we using for the connected descriptor? So here we're using a pointer. We have a pointer to the connected descriptor. And I'll explain in a little bit why this is important. In process-based server and event-based server, we just had a variable that we will just pass to the child. All right, so once again, we have this, this struct to, and this is where the accept system call will store the client information. So we have it. Sorry, this is where the client information will be stored, and this is just to ensure that we have a big enough client address variable. So here we use the size of operator, set the client length, and then in accept. So now we are using a dereferencing here because we have a pointer to the connected file descriptor. So whatever accept is returning, we're storing it using dereferencing So we have a listen file descriptor. This is where accept will store the IP address and the port of the client, as always. And then we are telling the accept system call, how big is our client address data structure. Otherwise, accept can make some wrong assumptions about what kind of client is this, IPv4 or IPv6, something like that. So once we do all that, once we have a connected file descriptor, once again, this is a while one loop, and this will happen over and over. And the server will block in accept each time. But before it returns, it's going to create a thread. And it's going to pass a pointer to this type. Second argument is null. Now, the function that the thread will run is called thread, and that's the function that will do the client side of the work. And then it's going to pass an argument, connected file descriptor. And connected file descriptor is a pointer, so it works. And the thread routine, so we call it the thread routine. The thread needs to know what to run, right? When you create a thread, what should it do? With fork, if fork equals 0, whatever was in the brackets would be executed by the child. So here we have a thread routine. So the child, whatever argument is passed, so we pass a pointer, right? So we pass an argument. This is the last argument. This is passed to the thread routine. So we are passing a pointer. So what the thread routine is doing inside the thread routine, we are casting it to integer type for safety, and then we are dereferencing it to get the integer connected file descriptor. Now it remains a mystery why we are using a pointer to the connected file descriptor. Not only that, we are actually doing a malloc here. So we are allocating a new integer on the heap, this time for the connected file descriptor. We didn't do that with process-based server or event-based server. Once we have the connected file descriptor, we're doing something different than join. So pthread join, whenever a thread is created, we call it's a joinable thread. So by default, every thread is joinable. A joinable thread is one that is reaped or killed by a different thread. So in the previous example, in the example of Hello World, the main thread would reap the peer thread that we created. Now, with client server applications, with concurrent servers, it doesn't make sense for the main thread to reap every client thread. We'll have a lot of clients. Some clients will do one thing, other clients will do something else. Some threads will run a long time, other client threads will terminate quickly. So we don't want the main thread to reap or wait for all the client threads. So there's a different way in situations like this. pthread detach, a thread can detach itself from all other peer threads. And once a thread calls pthread detach, no one can reap this thread and no one can kill this thread. And its resources will be reclaimed, freed up by the kernel when the thread terminates. When we have a joinable thread, the resources are only freed up by the kernel when a different thread uses pthread join to reap that thread. Okay, So here we are using pthread detach. So the thread is saying, okay, I'm detaching myself. I'm emancipated. I'm free. I'm on my own. So we free the heap space that we allocated for the connected file descriptor, and then we call our favorite, we play our favorite game, echo. So this thread is now hooked up to the client, and if there's another connection request, the main thread will accept it and create a new thread. So we'll have new threads this way. And then we close the connected file descriptor, because if we don't close it, it would be a leak. Okay, so now, we're running the thread in detached mode. It runs independently of other threads, read automatically by the kernel. We free up the storage and all that. So this is so easy. This is our client. This is our concurrent echo server using threads. Now I'll show you examples where we actually return something from the thread routine. But this is how we pass arguments. So when we have pthread create, whatever we supply, whatever we provide as an input argument here will be used as the input argument of the thread routine. So we've seen that. We pass a pointer, and then in the thread routine itself, we can, okay? So this is how the API works. You need a way to do certain things, and it may not be the cleanest way to do it, but this is how it happens. You can pass a pointer to a structure. You can have a structure with a lot of variables in it. If you want to pass, let's say, an array, or you want to pass a heterogeneous structure, and you can just pass a pointer. And the thread routine can dereference the different elements of the structure. So we know how to pass arguments to thread routines. We know how to start threads. We know how to create threads. We know how to, two different ways of reclaiming the resources taken up by threads. Now, what's the deal with this connected file descriptor? Now, I want you to think a little bit, and I'll get to it in a bit. So once again, what's the alternative? Suppose we just had a variable called, and we could have passed a pointer. Why did we not do this? Why did we not pass a pointer?
Because let's say if you might set two threads in the while loop before like you save the
right. All right, good. So I'm going to explain it a little bit for everyone. And this is an example of a race, and we sometimes call race, deadly race. It's not a the intent of the race here is not anything positive. It's deadly. So imagine that we pass not a pointer, but so we create on the stack of the main thread, we create a local variable called connectedFT, conft, and we pass a pointer to that address. First of all, like I said, conceptually, each thread has its own stack pointer. They share everything except this, and that, the stack and all that. But you can see already that we can break that abstraction. Operationally, we can break it. So if I pass a pointer to connectedFT, I am actually telling the thread routine, the peer thread, hey, you can go access my stack. Okay, so this is not a good practice, first of all. The race is, so if I pass a pointer to conft, imagine that the server goes back to the while loop and accepts a new connection. While this is going on, in the thread routine, the thread running concurrently is trying to dereference, sorry. So that would be, yes, same. The thread routine, inside the thread routine, the thread is trying to dereference the whatever is stored in conft. So one logical flow is trying to read something, the other logical flow is trying to update something, and we have a race. We don't know what will happen. If this thread doesn't run for whatever reason, the kernel decides, I'm gonna wait a little bit. What's the big deal? You're gonna play echo, right? You can wait for some reason. And the server goes and accepts another connection. Now, the thread routine will not see, we lost a client who was happy to play echo with us. We won't be able to play echo anymore. So that's a race. The thread routine is trying to read something, and the main thread is trying to overwrite it in the while loop by going back and accepting a new connection. And this is a race. Okay. To avoid that race, we create a new integer variable on the heap. The heap is shared, but that's all right. We are creating a new variable on the heap using malloc, and then we are passing the pointer to that variable. And that's a unique pointer for each client, for each thread. So now there is no race. So we have, we're moving on. We learned a few things about threads. So connection requests, once again, there's a listening server. The main thread, the peer thread, is a listening server, and clients are served by peer threads, and they all share data. They all run in the same context. In the context of the process. And certain things are separated out, like the stack and all that. But the entire virtual address space it's just one virtual address space. The kernel has all structures. It has file descriptors, tables, file tables, VM structs. There's only one copy. So threads share all process state except thread ID. And as much as we try to isolate the stacks of threads, you have already seen an example of how peer threads can access the stack indirectly of the another thread. So here's some information about detach. At any point in time, a thread is either joinable or detached. Joinable thread can be read and killed by other threads. And join, using pthread join, there's a lot of problems in high performance computing, in parallel computing, that require the use of join as a programming pattern. I'll give you an example in a little bit. Detached thread cannot be read or killed by other threads. So in our client server application, this is the proper pattern, the proper way to do that. The default state is joinable. And we must be careful to avoid unintended sharing. For example, passing pointer to main thread stack, we are giving peer threads an opportunity to mess up the stack of the main thread. Okay, thread safety is something we will do it in the next lecture. So imagine you have, why do you need join? So let's say you have a number of threads that do something. And once they all do their work, we need to do some processing here. And this is common in deep neural networks, machine learning, analytics. You divide up the work, data among multiple threads. Each thread in parallel analyze the data, their part, whatever data was given to them. And then you do some, let's say you combine the results of all threads, and then you spawn the next phase, right? So machine learning algorithms work like that. You have iterations. In each iteration, you do some computation, and then you figure out, what has you do some kind of a reduction operation. A simple example of reduction is that each thread sums up a portion of the array, and then you sum up the whole thing before you move on, right? So there's a lot of programming, a lot of interesting problems that have this phase behavior of where you need to join before you move on to the next phase of parallelism. And then detach is what we already looked. Why we need detach? Because we don't want the main thread to wait for all the clients to. There is no reason for the main thread. Main thread should go back and accept a new connection. There's no reason for it to reap other client threads who want to play echo. So threads are more efficient than processes. The programmer might not see this, but when we execute things, when we talk about performance, clearly threads are more efficient than processes. Easy to share data structures, but there's a problem. Sharing is not, at least in computer systems, sharing is not an easy thing to do. So unintentional sharing can introduce errors. The ease with which data can be shared is a strength, but it's also a weakness of threads. And that's why we're going to spend probably 3 lectures understanding synchronization to shared variables. And they're hard to detect by testing the races. For instance, the race here, it's subtle. It's, if I showed you the code with conft and a pointer to the thread routine, you might not have been able to tell that there'd be a problem or no. It takes a while. It takes an inspection, investigation. So this is a summary of our 3 approaches. So at this point, we have 3 concurrent servers: process-based, event-based, thread-based. So the other thing we want to do today is we want to understand really what is the meaning of sharing. What does sharing mean? What exactly is a shared variable? It's not that straightforward. So the question is, which variables in a threaded C program are shared? And the answer is not as simple as, the global variables are shared, and per stack variables that are on the stack are private to a thread and they are not shared. So we need to answer a few questions. What is the memory model for threads? How many instances of variables are mapped to memory? And how many threads might reference each of these instances? And we'll see that a variable X is shared if and only if multiple threads reference some instance of X. So what do I mean by that? So So multiple threads run in the context of a single process. Each thread has its own separate context, stack pointer, program counter, all that. All threads share the remaining process context. Operationally, this model is not strictly enforced. We have seen that already. Time and again, I've told you that. This is conceptually, we want this. Operationally, we can break this abstraction and we can access the stack of other threads by using pointers as arguments. The only separate thing is register values. But any thread can read and write the stack of another thread. And this mismatch between conceptual and operation model leads to errors. So let's look at an example program to understand sharing. So we have a global variable called, this is a pointer to a array of strings. So it's a double pointer. This is a global variable. It is stored in the global data segment or special region of virtual memory that we've seen before. Then it has this is on the stack of the main thread, a variable called I. And then this is also on the stack of the main thread ID. And then there are two strings, an array of strings that are also on the stack of the main thread. So here we're doing something that we shouldn't do, but this is an example. So we're assigning this array to this global variable. So it's saying pointer equals messages, right? So we have a global variable and we're assigning it what is on the stack of the main thread, pointer to the start of the messages array. And then we have a for loop, and we create two threads. We pass the pointer to the thread ID, null thread routine, and as argument, we are passing the integer I. Okay. And we are casting it to a pointer, it doesn't really matter. The thread routine doesn't care if it's an address or an integer, as long as we know what we're doing. And in the thread routine, what we are doing is creating a new variable. So my ID is on the stack of each peer thread. So we have two threads that we are creating. So we are creating two threads here. In a for loop, we are creating two threads. And each thread will have its own copy of my ID on the local stack. What? No, I don't want to dereference it because I'm passing an integer. I'm passing an address. So a pointer is an address, right? A pointer is an address. Because I know what I'm doing, that I'm just casting it. I know that this is not an address of a memory location. I know it's an integer, it's a loop counter. If I was passing a pointer as, an address of a memory location, and then if I do that, that's horrible. I know I'm passing an integer, and I can safely use it as an integer, the power of C. All right, so then I have a static variable count equals 0, and static variables they have a local scope. The scope of the variable count, CNT, is limited to the thread routine, but they're really treated in all other ways the same as global variables. So there is only one copy of CNT in the address space. So the compiler will ensure that there is only one copy of the variable count. And its scope is limited to, so this variable here is also static, but it's implicit. When you declare a variable outside of any thread, any routine, any function, it's implicit that static is added to it. You don't need to do it explicitly yourself. And static means storage duration. We did that, I don't remember, lab 3 or 2, I don't remember. So the variable is alive for the entire duration of the program. This is what static means. So here static is implicit. The compiler will do it for you because it's outside. And here, you're doing it yourself. Because for some reason, you want to limit the scope of this variable to this function thread, but you still want to have a single copy of the variable and want to treat it as a global variable. So then I have a printf statement that prints my ID, which is the local to the thread routine, it prints the global variable. So each thread will print one string, right? The index of the array is my ID. Now notice that indirectly, I have given the peer thread access to the stack of the main thread. Okay. Now I should not do that in real life, but this is just an example to show you. So PTR is a global. The function is legitimate for the function, the thread routine, to access it, but it really points to something that is local to the stack of the main thread. So indirectly, peer threads have access to, once again, operationally, this model is not fully enforced, that each thread has its own local stack. So here, indirectly, each peer thread can access this array messages, which is on the local stack of the main thread. Okay. And then we are doing a pre-count. Sorry, we're doing a incrementing count using the prefix notation. So we'll see in a little bit which variables are shared and which are not. So global variables, there's only one instance of any global variable in virtual memory. Local variables, each thread stack contains one instance of each local variable, and variable declared inside the function, these are variables that are declared inside the function without the static attribute. So like this one. Right? So each thread will have its own local copy of this variable. And then there are local static variables. Virtual memory contains exactly one instance of any local static variables, and these are variables that are declared with a static attribute. I want to treat the variable as a global variable, but I want to limit its scope to the thread routine. So here's a global variable. There's only one instance. These are local variables to the main thread. So we are going to use the notation I.m and messages.m to remember that variable I is local to main thread. Variable messages is local to main thread. So my ID has two instances, one corresponding to each thread, myid.p0 and myid.p1, peer thread 0 stack, peer threads 1 stack. And then we have the local static variable count. This is in the dollar segment. So let's fill this table now to understand sharing. So here's the variable instance. These are all the variables we have in the program, referenced by the main thread, referenced by peer thread 0, and referenced by peer thread 1. So help me fill this table. Pointer, is it referenced by the main thread? Yes? Referenced by peer thread 0? Yes, indirectly. Oh, sorry, not directly, because it's a global variable. Referenced by peer thread 1? Yes. What about count? Main thread? So what about I.m? So it's this variable I. This is tricky. So we have I. Are we referencing it or no?
Aren't we passing it by copy to the thread? So we're not directly referencing it, but referencing the copy of it.
Yes. All right, so let's leave it for the moment. What about messages.m? I think this will clear up. When we reach the end, you will see something, and we'll come back to the blank one. So messages is referenced by the main thread? Sure, right? I mean, it's created in the main thread. What about thread 0 and thread 1? So indirectly, using pointer, they are accessing it's just a pointer, right? It's just, they have the address. The address is all you need to access something. So what about myid.p0 and myid.p1? Why is that? Yeah. So pass by copy, pass by, this is 2300, you should know it by heart. Pass by, at least Charles tells me. So you always pass by copy. So here we are not passing a pointer. If we pass a pointer here, we would be sharing. And the thread routine dereferences that pointer, then it's sharing. But here we're just creating a copy and passing a copy. So everything else is correct and kind of straightforward. So which variables are shared? A variable is shared if and only if at least one instance of the variable is referenced by two threads, two or more threads. So our notion of sharing is now concrete, hopefully. Yes, a variable is shared if multiple threads reference at least one instance of X. And wherever there is sharing, we have to be careful. It's really hard to, the reason it's error prone and hard is because when programmers, they're writing programs, coming up with tables like this, and you want to focus on your programming part, not on making these tables and understanding which variables, and things can go wrong. So we will enforce a discipline using synchronization. Okay, so pointer count and messages are shared because there is a yes, at least. So pointer count and messages. And messages is the toughest one. If you just look at 1 million lines of code that someone else wrote, and you have to figure out what is shared, what is not shared, and they're using pointers like that, creating a global variable and then storing the address of something on the stack, it becomes really difficult. So yeah, so introduce a possibility of synchronization errors. So we want to understand synchronization. Let's look at this program, which we call bad count.c. So something is wrong with it. Otherwise, we won't call it bad. We call it good count or something. So we read in some number from the keyboard, which is the argument to this function. We create 2 threads, and to each thread we pass the pointer to this this variable, and then what the thread is doing is just adding up all the numbers together. So basically, what we should expect is 2 multiplied by n iters. So argument 1 is passed from the command line, this n iterations. Each thread sums up I equals 0, I is less than, sums up 0 to n iters, and then we join, and then if the result is not equal to 2 multiplied by what we expect, we print something is wrong with it, otherwise we print something okay with it. Now here we are passing a pointer to something on the stack of the main variable, but that's all right. So why is it all right here, but it wasn't all right with the connected file descriptor? Because the main thread does not update it. Because the main thread only, before creating the threads, it assigns it a value, whatever it reads from the keyboard, and then it doesn't touches it. And that's why synchronization or concurrent programming is hard. The same thing is not all right in one place, but it's all right here. So the interleaving of loads and stores and updates and all that, and analyzing programs, it's really a mess if we don't properly discipline ourselves. So what is wrong with this program? So if I run it, sometimes I get the correct output, and sometimes I don't get the correct output. So what is going on here, right? So I have 2 threads. We're both trying to take the sum from 0 to something, and it is count is a, oh, I should mention this. Count is a global variable, and I've used I've declared it as a volatile integer or long. Volatile means that each thread will read the copy of the value of count from memory. So the compiler will enforce that every read, every load of the count variable happens from memory. So everything in the so it won't be stored in the register file, because the register file is private to each thread, right? It is part of the thread context. So we are using volatile to tell the compiler, look, this is a shared variable, and we always want to read the most up-to-date copy from memory, and we always want to store the thing count all the way to memory. So we're giving up the register file so we can count, so we can do 2 multiplied by whatever. Now, sometimes I get the correct value, sometimes I don't get the correct value. I want to figure it out. So if I use this assembly for this for loop, so we want to look at the assembly code, and we want to understand what is going on. So each thread is executing this for loop. So I don't want to go to the assembly, but we set up the loop using head. So what we're doing here, if n iters is 0, then we don't want to do anything. We just want to get out of the loop. So here we are loading count, updating count, and storing count. So each thread, inside the loop, each thread reads the value of count, updates it, and stores it to memory. So if this is what's going on inside, count plus plus, right? Actually, it's not doing a sum. I'm sorry, it's not doing a sum. It's doing 2 multiplied by n it is. So whatever, I said it wrong. It's not doing a sum. It's doing something. You see what it's doing. From 0 to n it is, it's doing count plus plus. So it's counting the number of elements from 0 to n it is, and then multiplying it by 2, because there are 2 threads. But essentially, count plus plus means first reading what is the current value of count, adding 1 to it, and then storing it to memory. So count plus plus is the same as count equals count plus 1. So you want to read, you want to update plus 1, and then you want to store the result. So 3 things are happening in this one high-level C statement. And those 3 things are loading count, updating count, storing count. And then we have the tail, where we do the tail end of the loop, where we, if we need to loop back or we need to get out of a loop. So, and here they are using something called IP relative addressing. So to load the program anywhere in memory, for security reasons, they actually use this kind of addressing, where you can load the program anywhere in memory, and where count is stored is actually relative to the instruction pointer. So this is called position independent code. Okay, let's not get into that. This is the assembly. If you want to read more about it, this will be the last lecture when we do on linking, PC relative, program counter relative addressing. So you can load the program anywhere, and you know the distance from the program counter to the global variable. So you don't have to load the program at the same location in memory all the time anyway. So what is relevant to our discussion is there's a head of the loop, tail of the loop, and then the meat of the loop has 3 operations: load, update, store. So when we are running multiple flows, any sequentially consistent interleaving is possible between the instructions that are being executed by the 2 threads. So here, each thread will execute. So remember, we see that we call it LI, UI, SI. So this will be L1, U1, S1 for thread 1, and L2, U2, S2 for thread 2. So here is one possible interleaving. So thread 1 executes the head, then the 3 instructions, and I've colored these instructions for a reason. I call it the critical section. And then thread 2 execute head 2, load 2, update 2, store 2, and then the 2 threads are one after the other called the tail, execute the tail end of the code. So if you look at the code here, we are using RDX to store count. So RDX initially, when thread 1 loads RDX from memory, it has the value of 0. After the update, it has a value of 1. And after the store, it has a value of 1. And count, which is in memory, because we're using volatile, at this point, it's 1. Now thread 2 comes along and does the same 3 things, but when it loads count into RDX, which is 2, its own copy of RDX register, it loads 1. It updates it to 2, and it stores count back to memory. So everything is great. This is an interleaving that we love to have. This is a sequentially consistent interleaving. Sequentially consistent means that there is one interleaving of instructions executing one after the other. Okay. Now, the key idea is that any interleaving is possible. You're not likely to get this all the time. The kernel might do its own scheduling inside, and you might have H1, L1, H2, L2, U2, whatever, right? So here's another interleaving. This is okay. So here we have head is the head portion of the instruction to execute first for thread 1. Thread 1 loads, all good, 0. It updates, all good, 1. But before it can store, thread 2 comes along, loads the value, which in memory is still 0, because thread 1 hasn't stored the value yet to all the way to memory. Thread 1 then stores the value to memory, so it becomes 1. At some point, thread 2 updates its local copy of the value, which is 0 RDX, so it was 1, and then it stores. So both threads essentially store 1 to the same location in memory. So notice that the colors tell us what the problem is. So this is a sequentially consistent interleaving that is perfectly legitimate. Nothing stops today's systems to have this interleaving, because the kernel might decide at this point, look, I'm done with thread 1. I'm going to execute thread 2 now, for whatever reason. I mean, whoever wrote the kernel, whatever. And then it says, all right, thread 2, I'm not happy. I'm going to bring back thread 1. And so this interleaving, the green portion, the critical section, is interleaved with the critical section of the other thread. And where we have this interleaving of critical sections, we have a problem. Here, the critical sections are running atomically, sort of, not atomically as in one instruction, atomically in the sense that the 3 instructions execute to completion before the purple starts running. So there is no interleaving of instructions between the critical sections of the 2 threads. But here we have this interleaving, and we have a problem. So here, once again, count is initially 0. So this interleaving again is problematic, possibly because the green color and the blue and the purple is interleaved. So initially it's 0. Thread 1 loads 0 in RDX. Thread 2 loads RDX, loads count in its RDX register. There is only one RDX register physically. This is interleaving provided by the kernel. Thread 2 does the update in the register. Thread 2 stores it. Thread 2 stores 1 in memory. Thread 1 updates. So what would be RDX1? Thread 1 doesn't know about this, right? Thread 1 only has this in RDX. It was loaded from memory, right? It already did the load operation. So when it updates it, it does 1, because it hasn't seen this. You know, you don't do a load operation and then, you know, sometime later, let me do it again. You know, it's not funny. Right? You do it once, right? So you do it here, do the update, and then thread 1 stores it 1 in memory. So we know now that the interleaving of critical sections is problematic. Now, critical section relative to a specific variable here. The variable is count, and count is shared because if we look at the code, it's a global variable, and its instance is being referenced by more than one thread. So we know what a shared variable is. Its instance is being referenced by more than one thread. Once we know what a shared variable is, next we identify the critical section relative to that thread. And now we know that next thing, if there is an interleaving of critical sections from 2 threads, from the execution of 2 threads, we have a problem. Any sequentially consistent interleaving of instructions is possible. We may get lucky and get the right answer. Most of the time, we will be unlucky. Now, the way we want to understand further our understanding of critical sections is using something called the progress graphs. A progress graph depicts the execution state space. It's a multidimensional Cartesian coordinate system. Here we have two threads. So we have thread 1 here on the x-axis and thread 2 on the y-axis. And any point here means the state of the execution. So this means thread 1 has finished executing the load instruction, and thread 2 has finished executing the store instruction. So this way we can draw a trajectory on the progress graph, and we will figure out where exactly is the problem. So obviously you cannot go backward, you cannot go in this direction, and you cannot go diagonal, because that would be executing two instructions. So we are assuming that each instruction is atomic. You cannot execute two instructions in one step. So here's one possible trajectory. And a trajectory is a sequence of legal state transitions that describe one possible execution of the thread, right? And so here we have the critical section. So we have the critical section for thread 1 here, and we have the critical section of the thread 2 here. And what we want to enforce is that instructions in critical sections with respect to some variable are not interleaved. And the set of states where such interleaving takes place, we call them unsafe regions. So here is our unsafe region. We don't want any trajectory to enter the unsafe region. As long as you're in the boundary, as long as you're skirting the unsafe region, that's all right. But when you enter the unsafe region, there's a problem. So, for instance, a trajectory is safe if it does not enter any unsafe region. So here is a safe trajectory. It tried to enter the unsafe region, kind of at the boundary, but it quickly just, So this is a safe trajectory. So thread 2 does all the update. Thread 1 executes the head portion of the loop, and then thread 2 does the store before thread 1 does the load. So this load here, this load happens after the store of thread 2. So this is a safe trajectory. This trajectory, because it's red, there must be a problem. It enters the unsafe region, and you can see what the problem is. The thread 1 is doing the update, and the variable count is in its register. And thread 2 loads the stale copy of count from memory. So the interleaving of, when you enter the unsafe regions for the remaining, and for your assignment and for the rest of your life, we don't want to enter the unsafe. We want to force the kernel. The kernel doesn't know this. The kernel did not create the count variable. We created the count variable. We know that with respect to the count variable, there is a critical section and there is an unsafe region. The kernel doesn't know that. It's just scheduling things the way it sees. It sees a sequence of instructions. We want to force the kernel to stay out of the unsafe region. And we want to do that with synchronization primitives called semaphores and mutexes. Now, I don't know if we can do this today, but the key idea you take away from today's lecture is we want to force the kernel to stay out of this unsafe region. Don't enter this region. And we can do that because we created the count variable. We wrote the application. A trajectory is correct if it is safe. When we talk about concurrent programming, not all trajectories are safe. They are possible, they are feasible. Feasible means it could happen. Nothing stops us, nothing stops the kernel from making this happen, but it's not correct. All right, so how can we guarantee safe trajectory? We must synchronize the execution of threads using, and they can never have an unsafe trajectory, and we need to guarantee mutually exclusive access to critical sections. And the classic solution is semaphores, which we will do on Thursday. So we'll start looking at the synchronization primitive that will let us tell the kernel, look, stay out of this region, and then you will use these to write a concurrent proxy cache in your assignment. And all right, that's it. See you on Thursday.